Hi everyone, welcome to the course on measurement and instrumentation, and today is the fourth lecture of our ninth week where we are going to discuss about filters. We are discussing our fourth module where we are talking about different signal conditioning circuit and signal conditioning systems. So, filter basically is very crucial part of any signal conditioning circuit because it decides that which portion of the signal will pass and which will not be passed or which will be attenuated. Okay? We have already seen amplifiers and attenuators in our previous classes. Okay? So, a filter selectively pass signals within a defined frequency band while attenuating components outside that particular band. Okay? This will help in suppressing unwanted noise. It also helps in avoiding any kind of interference and undesired spectral components in a signal. Okay? So, filters perform bandwidth limitation prior to the signal processing or analog to digital conversion, and this bandwidth limitation is very crucial for various circuit aspects that we will see in this particular lecture. Okay. So, this actually helps in minimizing aliasing effect. This also improves signal to noise ratio significantly and ensure accurate representation of the desired signal spectra. Okay. So, this is one typical example that how a filter helps in reducing, at least if not removing, noise in a signal. Okay. So, this is a signal, input signal with certain level of noise, okay, and the filter here is attenuating high frequency noise component from the input signal and allowing only the desired low frequency signal to appear as a cleaner output. Okay. So, this is a typical two-port diagram for a filter. Okay, you can see that there is a source and a load, and this output has to be cleaner in terms of noise and other unwanted signals. Okay. So, an electrical filter is excited, say for example, by a sinusoidal source of varying frequency, allowing analysis of its frequency dependent behavior. The filter is designed basically to transmit a selected frequency component with minimal attenuation while significantly suppressing any unwanted frequency at the output. Okay. The basic electrical filters are of two forms as regards the component constituting them. Okay. You can have either passive filters and you can have a active filter. Okay. So, passive filters, as the name suggests, use only passive circuit elements like resistance, capacitance and inductance, while the active filters will use active elements like op amp in addition to passive components like resistor, capacitor and inductors. Mostly we will try to avoid inductors, but will focus mostly on op amp and resistors and capacitors. Okay. So, there are different type of these filters. You have low pass filters, you have high pass filters, band pass filters and band reject, or sometimes also known as notch filters. So, this is a typical characteristic of low pass filter. You can see that, say this is the frequency range. Okay. So, I am writing it as a frequency range, okay, that you want your filter to pass. All right. So, this is a low pass filter. So, it is passing frequency in the lower region. Okay. So, high pass filter, as the name suggests, will pass only higher frequency signals. Okay. And you can see that the lower frequency component is getting suppressed. Band pass filter will allow signals to pass in particular band. Okay. And band reject or notch filter will allow to pass signals of lower and higher frequency, and it will reject certain range of frequencies. All right. So, if you see, there are three different components in this filters or three different regions of this filter: frequency versus gain curve. Okay. You have pass band, in which pass band means the frequency range where the signal passes with nearly constant or at least maximum gain. You have a cutoff frequency. We will see what is a cutoff frequency for particular kind of signal, but you can say that it is also known as break frequency or a 3 dB point. It is the frequency at which the output amplitude drops to about 70.7 or 0.707 of its pass band value. So, you can say that, say if it is A, okay, So this is, say for example, around 70% of this A, okay, or 70.7% of A, okay, and this is the value that I was just mentioning about the break frequency or the cutoff frequency, okay. You can say that the power falls for this particular signal by 3 dB at this particular point, okay. Then you have a reject band or a stop band, okay. So this is the frequency range where the signal is not getting passed. You have seen that for low frequency, above certain frequency, we were not allowing the signals to pass through the filter. Similarly for high frequency and other high pass filter and other filters also similar characteristics were observed, okay. So if I talk about an ideal response of these filters, you can see that a low pass filter, okay, will have a pass band something like this, means that it is actually passing all the frequencies below some reject band or a cutoff frequency, okay. So it is allowing all the frequencies below omega c to pass, and above omega c it is rejecting all the frequencies. So this is the pass band and this is the reject band, and of course we have seen that this is not the actual filters will not obey this, and this is actually a very ideal response, and of course we will try to reach this gain versus frequency curve as much as possible, but that is not always possible, okay. So you may have curve something like this that we have already seen, right. Similarly for high pass filters, you have a reject band in frequency regime where this frequency, say omega, is less than omega c, and above omega c you have a pass band, okay. Similarly for band pass filter, you have a region of frequencies which can be passed through the filter. Say here, say omega c1 to omega c2 can be passed through the filter. However, this particular filter rejects anything less than omega c1 and anything above omega c2, all right. Similarly, band reject filter will have a pass band in the frequency regime which is less than omega c1, and anything above omega is greater than omega c2, all right. So this is the pass band, and in this range omega c1 to omega c2, this frequency is rejected, all right, and that's why this is the reject band for the filter, okay. So these filters can be designed, as the name suggests, passive filters. They can be designed by using passive components like resistor, capacitor, inductor and so on, okay. So this is typical low pass filter, okay, just made by using R and C, a resistor and capacitor, okay, where the output is taken across this capacitor, okay. The transfer function for this kind of circuit in terms of Laplace form, we can write that E naught or this E output, okay. So it's up to you, you can use E naught or E out as per your convenience, divided by EI, which is your input, as 1 by SC. Of course, when you are taking this Laplace, so it is E naught by E1 in the Laplace domain only, 1 by SC into R plus 1 by SC, which is equal to 1 by 1 plus SRC, okay. Now this RC is usually represented by tau, which is your time constant, and this transfer function is given as 1 by 1 plus S tau, all right. Now the sinusoidal transfer function of a low pass filter can be simply found by replacing this S by j omega, okay. So in that case, E naught by EI j omega is equal to 1 by j omega c, very similar to what we have seen, divided by R plus 1 by j omega c. Now this is equal to 1 by 1 plus j omega tau, again replacing RC by tau, okay. So gain of this signal or the transfer function can be given as the mod of this E naught by EI j omega, which is given as 1 by root 1 by 1 plus omega RC square, or 1 by under root 1 plus omega tau square, okay. This is a typical gain of a low pass filter, okay. Now this gain drops to 0.707 at cutoff frequency omega c, okay. So you can simply find a gain by equating this particular gain 1 by under root 1 plus omega RC square with 0.707, okay. Or the cutoff frequency can be simply calculated by this particular formula, and the cutoff frequency is given as 1 by 2 pi RC or 2 pi tau. Okay. Now, this low pass filters, for example, is very crucial for several applications. I mean, I am giving just one example. You can think that other filters have also application in the similar line. Okay. Now, suppose a dynamic strain varying at a frequency of 1 hertz is being measured by certain transducer, say a strain gauge. There is a possibility that the output measurement circuit can pick up signals of 50 hertz, which is of course the supply current on which it is. I mean, there are a number of 50 hertz fields around any strain gauge because it is our household supply. Okay. So, you cannot avoid that if you are not having a proper shield and other things to avoid any kind of interference with 50 hertz signal. So, it is always possible to pick up this 50 hertz power line. Okay. So, now you have a strain gauge which is generating a data at 1 hertz and you have a signal nearby which is 50 hertz. So, it's very easy to get contaminated this 1 hertz data with the 50 hertz data. Okay. So, in that case you can use RC low pass filter as you can see over here. Okay. Now, you can understand that when you have this kind of arrangement, you always want to avoid any higher frequency component and want to trace down the 1 hertz line or 1 hertz data into the signal. Okay. So, this figure shows the input signal to the measurement system, which consists of a desired strain induced signal at 1 hertz along with of course the superimposed 50 hertz power line, and it typically can be something like this. I mean, depending on your signal is now 50 hertz, which is modulated by say 1 hertz data. Okay. So, now what you need is basically a low pass RC filter that can be designed like something like this, so that the desired signal of 1 hertz is reproduced faithfully while the higher frequency signal of 50 hertz or so is attenuated by the filter. Okay. So, usually this is mostly suitable for this kind of signals. However, you may also require filters which only pass high frequency component, and for those kind of circuits you need a high pass filters. Okay. So, this is a typical high pass filter. Now, configuration is something like this. You have this capacitor and now you are taking output across this resistor. Okay. So, in this case the transfer function can be written as E naught by EI as R by R plus 1 by SC, which is equal to tau S by 1 plus tau S. Again, tau is equal to RC here. Okay. So, the sinusoidal transfer function similarly can be found by simply equating this or replacing S with j omega, or E naught by EI can be written as j omega RC by 1 plus j omega RC. Okay. Or this is equal to 1 by j omega tau. Okay. Now, gain can be found from this equation as omega tau by under root 1 plus omega tau square, or 1 by under root 1 plus 1 by omega tau square. Okay. Similarly, the cutoff frequency can be found by equating omega c with the 1 by RC, and cutoff frequency in hertz can be given as 1 by 2 pi RC or 1 by 2 pi tau. Alright. Similarly, band pass filters can be designed using R and C, and this is a typical band pass filter. You can understand it like cascading of a low pass filter with a high pass filter. Okay. So, this is say a high pass component and this is the low pass component that we have just seen. Okay. Now, just cascading them together, okay, can give you a band pass filter. Okay. In this case, there is a pass band with lower cutoff frequency FC1, and you also have a upper frequency cutoff at FC2, so that this particular band in between FC1 and FC2 can be passed. Alright. So, in the pass band region, the circuit behaves almost like a resistive network or a kind of voltage divider, something like this. So, at this particular pass band, you have this capacitor as open and this as short, and you have this kind of configuration. Okay. Now, at frequency below the pass band, it behaves like a high pass filter as shown over here. Okay. Now, above pass band frequency, the capacitor C2 behaves as a short circuited and the circuit behaves like a low pass filter. Okay. So, if R2 in this case is greater than 10 R1, okay, FC1 is given as 1 by 2 pi R2 C2, while FC2 is given as 1 by 2 pi R1 C1. Alright. Now the low pass and high pass filters are connected in cascade. As we have seen, the transfer function can be simply given as just by multiplication of them. So, or 1 by 1 plus s tau 1 multiplied by tau 2 into s by 1 plus s tau 2, the two transfer functions of low pass and high pass. Okay, we have seen that tau 1 is equal to r1 c1 while tau 2 is equal to r2 c2, and tau 2 is of course greater than tau 1. Okay, and gain in the pass band can be simply given as r2 by r1 plus r2. Okay. Similarly, the notch filters can be designed, and for designing a notch filter usually we take help of a 20 circuit. Okay. So, RC band stop or band reject filter uses a Wien bridge circuit of a 20 circuit, as you can see over here. Okay. At very low and very high frequency, gain is almost unity, and in between there is a frequency where gain becomes 0. Okay. So, it rejects or attenuate one specific frequency called the notch frequency f naught, and all other frequency passes with a very little attenuation. Okay. So, in this 20 type of notch filter, the notch frequency can be given as f naught equal to 1 by 2 pi RC. Okay. However, we have seen this several RC kind of filters. However, they might not be that useful for practical applications, particularly when you want a sharper cutoff and you want any attenuation beyond the pass band. Okay. Usually LC filters are preferred over the RC filters. Okay, because it again it provides you a sharper cutoff and also prevent any attenuation in the pass band. Okay. So, let us see some example of LC filters as well. Okay. So, at low frequencies particularly you can see there are 3 different configuration. I am calling this L section. Okay. You have this inductor and capacitor. This I am calling as T section. This is very similar to what you have seen for attenuators. We have already seen the L configuration, T configuration and the pi configuration. This is very similar to that. You have this L configuration or L section, you have this inductor and capacitor connected like this. You have T section where you have 2 inductors and 2C is placed over here, and pi section as these 2 capacitors are there, and this is the inductor value. Okay. So, at low frequencies the inductance presents a short while the capacitor is open circuited with the output almost equal to the input. Okay. So, at higher frequencies, the inductance present at a high series impedance while the capacitor is short circuited. And again, if you do not remember, these things are coming from XL and XC. XL we know that it is 2 pi FL and XC is 1 by 2 pi FC, right. So, when frequency is very low, okay, when frequency is very low, XL will be almost equal to 0. Okay, and XC will be equal to infinite. Okay. So, at and similarly when you have this F as very high, okay, this will become infinite and this will become almost 0. So, at higher frequencies the inductors present a high series impedance, okay, while the capacitor is short circuited, as you can see. Okay, and this gives you 0 output. Therefore, the circuits, these circuits are basically a low pass filter. So, you have seen 3 different configurations for a low pass LC filter. You have L section configuration, T section configuration and a pi section configuration. Okay. Now, the characteristic resistance, it is one of the important terminology for LC filter, can be given as under root of L by C. Okay. So, in LC filter the source impedance and the load impedance are made equal to the characteristic resistance R naught, so that the filter transfers maximum signal power and maintain its proper frequency response. And that is why characteristic resistance of any LC filter is very crucial, and you can see that it can be found by simply dividing the inductance value with the capacitance and taking its root. Okay. The cutoff frequency for this kind of filters can be given simply by 1 by 2 pi under root LC, or if I replace it with the R naught, it can be simplified as 1 by 2 pi R naught C. Okay. The stop band attenuation increases with number of stages. So when you increase the number of stages, the stop band attenuation will increase, and attenuation in dB can be simply written as 8.7 into n into alpha, where alpha is the attenuation factor and it can be given like this, and n here is your filter stage or number of filter stages present in the circuit. Okay. So similarly, you can use LC circuit to design high pass filters. Okay. So LC network acts as a high pass filter because this kind of LC network acts as a high pass filter because the series capacitance block low frequency while the shunt inductance bypass low frequency to ground, allowing high frequency to pass. Okay. So this is a typical LC band pass filter. You can see that you have an inductor and capacitor in parallel, and you have another configuration of inductance and capacitance in series. Okay. So at low frequencies, when f is much lesser than the f naught, okay, XL is equal to 2 pi FL that we have seen, and XC equal to 1 by 2 pi FC. So in this case, when you have low frequencies, the shunt inductor behaves almost like a short circuit, and the signal goes to ground instead of output, and low frequencies are attenuated, and in this case f naught is given as 1 by 2 pi under root LC. Okay. Now at higher frequency, when f is greater than much greater than f naught, if you see, XL becomes, when you have 2 pi FL, so f is very large. In that case, XL become very large, while in this case 1 by 2 pi FC, when f is very large, in this case XC becomes very small. Okay. So the series capacitor becomes almost a short circuit, but the series inductor has very high impedance, so it blocks the signal, and high frequencies are also attenuated, and you only have a particular frequency which is getting passed. Okay. So this is happening at a resonant frequency. We call it the f naught as resonant frequency. Okay. So at f equal to f naught, XL is equal to XC. Okay. So the series LC impedance is minimum and parallel LC impedance is maximum. So the signal passes through the filter, and signal cannot go to ground right now, and signal passes through the series path. All right. So in this case, the attenuation factor for LC band pass is again given by this formula. This alpha is given by 2 cos hyperbolic inverse into f by f naught plus f naught by f, where f is your operating frequency and f naught sometimes called center frequency or sometimes also called the resonant frequency. Okay. And the stop band attenuation increase again here with number of stages, and attenuation can be given as 8.7 into n alpha, where n is the number of filter sections while alpha is your attenuation factor. All right. So a band pass filter is characterized by its central frequency f naught, where the gain is maximum. Okay. And the bandwidth of these filters can be simply given as f2 minus f1, and f naught, the central frequency, is actually, it can be given as a multiplication of f1 and f2 under root, or f naught is equal to f1 f2 under root. Okay. There is one more term which is very crucial for these filters, which is known as the quality factor, and quality factor of this band pass filters are given as f naught by bandwidth, or f naught by f2 minus f1. Okay. So in this case, if you have high quality factor, okay, so when you have this quality factor as high, okay, so in that case, so when I say Q is high, okay, means that it is equal to, say, f naught by bandwidth, means that this bandwidth is narrow. Okay. Then only this quality factor is high. Okay. So when you have high quality factor, means you have narrow band, means that you have a very narrow band of frequency which is getting passed. Okay. And low Q means you have wide frequency range, means multiple frequency band is possible. Okay. So when this quality factor Q value is low, which is, say, value of 1 or even less, the filter can be built easily by connecting a low pass filter and a high pass filter in series or in cascade to form a band pass type response. When the Q value is higher, this simple method does not work well, so specific circuits has to be made, and when you have this Q less than 10, multiple feedback active filters are used, and when you have this Q greater than 10, you have state variable filter circuit that is preferred. Okay. Similarly, you can also make LC notch filters, or we call it band stop filter. You can see that a simple L and C in series, and when you take output across this load resistor, can work as a notch filter or a band stop filter. Okay. So, at low frequency, say very near to 0, the capacitance reactance is high. So, the LC branch acts open and the signal appears across the load, and at the resonant frequency, say f naught is equal to 1 by 2 pi under root LC, the series LC impedance becomes minimum, effectively shorting the signal to the ground. Therefore, the output voltage across the load becomes again 0, rejecting that particular frequency, or which is, we call it the notch frequency, and other frequencies are passed. Okay. So, this is how output across this load looks like. So, this frequency is getting transmitted, this is also passed. However, this particular frequency very near to this notch frequency is getting attenuated. Okay. So, this is a typical example of different RC and LC circuits. Okay. Again, all these that we have just discussed are passive filters, and we have seen that they are built up of resistance, inductance and capacitance. Although they are simple, they have actually several limitations. Okay. Like one of the important limitation of these circuits or these filters is that it cannot give you any kind of amplification. Okay. So, passive filter cannot provide any gain. The output signal is always equal to or even smaller than the input, and in many electronic systems signal amplification is required along with the filtering. Okay. Now, although the LC filters or LC based, maybe you talk about high pass or low pass, whatever filters, they were able to provide high or a sharp cutoff frequency. However, they have a requirement of inductors. So, all of them were having one or multiple inductors, and when you use inductors, particularly when you deal with IC and other things, it has a larger physical size because it is basically a coil. Okay. So, it requires a large size and they are also expensive. Okay. Therefore, they are not suitable for IC fabrication, and they are actually avoided in VLSI and IC designs. Okay. Usually, they also have magnetic interferences because they are coil, and any change in nearby magnetic field or any change in nearby currents can induce any other currents or magnetic field in these coils. So, usually they are avoided, particularly for on-chip applications. Okay. They also have a good amount of loading effect, because when you connect it to another stage, the frequency response may change and may cause distortion in filter characteristic. Okay. These passive filters also have loading effect. These are affected by source and load impedance, and when they are connected to another stage, the frequency response may change. Okay. And this causes distortion in filter characteristic. All right. They also have poor performances at lower frequencies. So, to achieve low cutoff frequencies, passive filters require very large inductors or capacitors, and when you require that kind of larger capacitor and inductor, even for non say chip application, say pure electrical applications also, sometimes it becomes impractical. Okay. Therefore, active filters are required. So, active filters, as I have mentioned earlier, also use active devices such as op amps, transistors, ICs, along with the passive component like resistors and capacitors. Okay. So, these active filters can provide you amplification. So, they can amplify signal while also can do filtering, and mostly the gain is of course greater than 1, and this improves signal strength and signal to noise ratio. At the same time, it is also filtering. Okay. So, no inductors are required. That is why I told initially also that we will study these active filters where we will avoid any kind of inductors. Okay. So, active filters generally use only resistors and capacitors with op amps. Okay. So, no loading effect, or at least minimum loading effect with the active filters because of the high input impedance and low output impedance of the op amp. Okay. It also provides you stable frequency response along with the minimal loading. Okay. These active filters also have better low frequency performance, which was actually difficult to achieve with the passive LC filters. So, therefore, it is very important to study about the active filters, and maybe in the next class we will continue our discussion on filter and will try to discuss the active filters which are made up using op amps and other active components. Thank you.